Today, we're going to show an activity called providing that gas has mass. This is part of our lesson on gases, particularly under Boyle's law. Let's start. Materials and procedure for this activity we use. A rubber balloon, a digital balance with a precision of 0.01 grams, and an optional balloon pump to inflate the balloon. We first measure the mass of the deflated balloon using the digital balance. After that, we inflated the balloon and measured its mass again. Here are the results. Deflated balloon mass detected was only around 0.001 grams. Inflated balloon in trial number 1, the mass was 0.002 grams. In trial number 2 and 3, the mass was 0.012 grams.
Bakit nangyayari ito? This proves a very important concept. Gas has mass. Even though gas is invisible, it is made up of tiny particles called molecules. When we inflate the balloon, we are adding air molecules inside. These molecules have weight or mass kahit sobrang liit. The digital balance detects the added mass caused by the air inside the balloon. This shows that air is matter, and like all matter, it has mass and occupies space. Why are the values small and inconsistent? You might notice that the mass increase is very small, and the values change a bit in every trial. This is because the amount of air we add is not exactly the same every time, and the balance is very sensitive, so even small changes in air pressure inside the balloon can affect the reading.
Today, we are doing activity 2 to demonstrate Boyle's law using a simple experiment with a marshmallow and a syringe. Let's start. Materials and procedure for this activity we use: a marshmallow and a syringe. Here's what we did. First, we placed the marshmallow inside the syringe. Second, we covered the hole at the end of the syringe to trap the air inside. And last, we pulled and pushed the plunger while observing what happens to the marshmallow. What did we observe? When we pull the plunger, the marshmallow expands or gets bigger. When we push the plunger, the marshmallow shrinks or gets smaller. Why does this happen? This happens because of Boyle's law, which states that as the volume of a gas increases, the pressure decreases, and when the volume decreases, the pressure increases. When we pull the plunger, we increase the volume inside the syringe. This lowers the pressure so the air inside the marshmallow expands, making the marshmallow bigger. When we push the plunger, we decrease the volume inside the syringe. This increases the pressure, squeezing the air inside the marshmallow and making it smaller. This shows that gases are compressible and that pressure and volume had an inverse relationship, which is exactly what Boyle's law describes. In this activity, we are going to demonstrate Charles' law, which explains how temperature affects the volume of gases. Materials and procedure for this experiment we use: a rubber balloon, tap water, hot water, and ice water. A tape measure. We inflated a balloon and measured its circumference. We placed the balloon in each type of water and measured its circumference again after a few minutes. Here's the result. Initial circumference 19 inches. After 30 minutes in the refrigerator, the balloon shrunk to 18 inches. After 3 minutes in hot water, the balloon size stayed the same at 18 inches. Why does this happen? This happens because of Charles' law, which states that the volume of a gas increases when temperature increases and the volume decreases when temperature decreases as long as the pressure stays the same. In cold water or the refrigerator, the temperature decreases, so the gas inside the balloon contracts, causing the balloon to shrink. In hot water, the gas should expand, which would normally make the balloon bigger. However, in our case, the balloon may not have expanded because the balloon could already be stretched to its maximum size, so it cannot expand further. Some air might have leaked out during the experiment, keeping the size the same. The temperature difference may not have been enough to cause a big change in volume. Today, we'll explore the combined gas law through a hands-on activity using every materials. This experiment will help us understand how pressure, volume, and temperature of gases are interrelated. Materials: 7 empty cans, nail polish remover, lighter, Empty plastic bottle, scissor, nail, sprayer. Procedure. Puncture it can using the nail, ensuring no sharp edges remain. This allows gases to move in out freely. Modify the plastic bottle. Cut the plastic bottle into two sections, one longer and one shorter. Assemble the structure. Align the cans in a row and connect them using the shorter section of the plastic bottle. This setup creates a series of interconnected chambers. Last, prepare the sprayer, puncture the bottle cap and insert a magnet. This setup demonstrates the combined gas law, which integrates Boyle's, Charles, and Gay-Lussac's law. It shows how pressure, volume, and temperature of a gas are related. Heating the cans. When the cans are heated, the temperature inside increases. According to Charles' law, if pressure remains constant, the volume of a gas should increase. However, since the cans have fixed volume, the pressure inside rises instead as per Gay-Lussac's law. Cooling the cans. Spraying the cans with nail polish remover, which evaporates quickly, causes rapid cooling. This sudden temperature drop leads to a decrease in gas pressure inside the cans. If the external atmospheric pressure is higher, it can crush the cans inward, demonstrating Boyle's law. This experiment visually showcased the relationship between pressure, volume, and temperature in gases. By manipulating one variable, we observe corresponding changes in other, reinforcing the principle of the combined gas law. Today, we are going to demonstrate an experiment called squashing the bottle, which will help us understand how air pressure and temperature affect gases. Materials for this experiment we only need a 1.5-liter plastic bottle and hot water. We fill 1/3 of the bottle with hot water. After a few seconds, we empty the bottle and immediately seal it with a cap. Then, we observe what happens to the bottle. What did we observe? After some time, the plastic bottle starts to collapse or get squashed inward on its own. Why does this happen? This happens because of air pressure and the cooling of gases inside the bottle. When we pour hot water into the bottle, it warms up the air inside, causing the air molecules to move faster and expand. When we empty the bottle and seal it, the remaining air inside starts to cool down. As it cools, the air molecules slow down and take up less space, creating low pressure inside the bottle. Since the air pressure outside the bottle is now greater than the pressure inside, the higher external pressure pushes against the bottle, causing it to collapse. Through this simple activity, we can see how air pressure works and why temperature plays a big role in gas behavior. This is the same principle behind weather changes, vacuum packing, and even how our lungs work. Now, we will perform activity B of squashing the bottle, which will help us understand how temperature affects gas pressure using the ideal gas law. Materials for this experiment we use 2 empty 1.5-liter plastic bottles, a plastic bag, a hammer, and ice cubes. Procedure. We put ice cube in the plastic bag and crush them using a hammer. We then place the crushed ice into the plastic bottle and seal it with the cap. Next, we shook the bottle to make sure the inside was truly chilled. Finally, we observe what happened to the bottle. Observations. After some time, we noticed that the bottle began to shrink or get squashed inward on its own. Why does this happen? This happens because of the relationship between temperature, pressure, and gas volume inside the bottle. Cooling the air inside. When we add crushed ice, the air inside the bottle gets colder. Cold air molecules move slower and take up less space. Lower pressure inside the bottle. Since the air molecules are now moving slower and exerting less force, the air pressure inside the bottle drops. External air pressure crushes the bottle. The air outside the bottle still has normal atmospheric pressure. Because the pressure inside the bottle is lower, the higher external pressure pushes against the bottle, causing it to collapse inward. This is a simple but effective way to observe how temperature changes affect air pressure, which is an important principle in the ideal gas law. These experiments show how cooling a gas decreases its pressure, leading to a visible change in the bottle's shape. This principle is applied in real life, such as in vacuum packing, weather system, and refrigeration technology. Today, we will demonstrate an experiment called a gaseous outlook to understand how air pressure in gases behave in liquids. Materials for this experiment we need a bowl, a drinking glass, and water. Turn the glass upside down and place it into the water. Then we lift the glass slightly while keeping the rim below the water surface and observe what happens. So for our observation, when we lift the glass while keeping it underwater, we notice that the water does not enter the glass completely. It remains partly filled with air. Why does this happen? These experiments show how gases occupy space and exert pressure. When the glass is submerged upside down, the air inside the glass gets trapped because air is less dense than water. As we lift the glass without letting go the rim go above the water surface, the trapped air prevents water from entering fully. This happens because air exerts pressure against the water. The trapped air pushes downward, counteracting the pressure of the surrounding water, so the water level inside the glass remains lower than outside. If we tilt the glass or let the rim go above the surface, the trapped air escapes, allowing water to rush in and fill the space. This simple experiment demonstrates that gases take up space and exert pressure. Even though we cannot always see them, this concept is important in everyday life. From how scuba divers manage air pressure underwater to how we breathe and how airplane cabins are pressurized. That's all for our experiment. Thank you for watching.